Hello everyone, here I would like to present our paper, Improving Robotic Grasping Ability Through Deep Shape Generation. Data-driven grasping method have become a dominant paradigm for robotic grasp planning during the past decade. However, the performance of these methods is greatly influenced by the quality of the training dataset. Though many grasping dataset have been proposed with more shapes, annotated grasps and sensory information, a well-trained network on existing dataset may still fail when facing to a new object. To solve this problem by improving the grasping dataset quality, like simply adding these failed objects into the training dataset to expand it, and retrain the model again. Or perform some data augmentation methods used in computer vision area like flipping, cropping, and rotation, will be expensive, tedious and non-systematic. Hence, the key question is how to improve the grasping dataset quality so as to enhance the graspability. Our solution is: we first propose an encoder-decoder network to map shapes into a low-dimensional feature space, then a systematic approach is proposed to generate new shapes that can improve the graspability. In detail, we first propose an acritic network, which embeds shapes into a low-dimensional feature space. In this feature space, shapes can be better encoded, interpolated, and generated. In shape generation, original shape's rarity and graspness scores are computed through outlier detection and grasp quality criteria. Then every two high-score nearby objects, which are rare for the whole grasping dataset, are grouped as a generation pair. Finally, the acritic network is used for shape generation through interpolation between two shapes' feature vectors. In experiments part, all the experiments are based on the GQCNN network index net 2.0. Since we only generate new shapes for grasping, others grasp planning network like GGCNN, GraspNet and so on can also be applied. Firstly, to see the effect of augmentation in detail, we separately augment 200 shapes in training dataset leveraging the feature of high rarity or graspness score shapes, and see the AP score improvement of objects with different rarity or graspness scores in the testing dataset. The relationship between selected high-score data, generated data, and AP score improvement is shown below. It shows that more selected shapes will result in more generated data with same scores, and further lead to higher AP scores improvement. Then to find the optimal augmentation ratio and augmentation limit, we randomly select 50, 100, 200 shapes from training dataset, and generate new shapes with different augmentation ratios. Here 1:0 means no augment is performed, and 1:2 means that twice the number of generated shapes compared to the original shapes are used for data augmentation. The whole 15 trained network on all datasets shows that the greater number of original shapes, the higher augmentation ratio is allowed. And blindly increasing generated data may cause bad performance. Finally, to validate the augmentation effect in real application, we augment 200 original shapes with 409 generated shapes, and train two GQCNN networks on before and after augmented dataset. Then we test these two networks with 8 everyday objects on real robot and 10 grasps are performed on each object. The average grasp success rate is improved from 68% to 86%. Here are one object's grasp results. Here are more objects' grasp results. Thank you.